In case of convex quadratic functions, we have f of x is given by 1/2 x transpose times q times x plus c transpose times x, where q is assumed to be positive definite, so we have the convex problem, right? Then we can explicitly compute the gradient, so the gradient at xk will be given by q xk plus c, right? And the k plus first iteration of the steepest descent method will be xk plus 1 is xk minus alpha k nabla k, where nabla k is given by this expression. If we denote by phi k of alpha, like we did before, this function of the step size alpha, which is given by f of xk minus alpha nabla k, and then alpha k is the minimizer for f of xk minus alpha times nabla k over alpha greater than or equal to 0, right? So, and then because we know that the gradient is given by q of xk plus c, we can actually write down this function explicitly and minimize it analytically. This function phi k of alpha, if we plug in all the data we have here about f and about the gradient, so if we plug it in, we can see that this phi k of alpha is actually a quadratic function of alpha, of a single variable alpha, where the coefficient for alpha square is given by this expression here, and because the matrix Q is positive definite, this coefficient is positive, then the coefficient for alpha is given by nabla k transpose times nabla k, and then we have a constant term f of xk. For this quadratic function of a single variable, we can easily find the minimizer, so this is the point where the derivative of it with respect to alpha is equal to 0, which is given by this coefficient here divided by 2 times this coefficient. The expression that we get for alpha k is nabla k transpose times nabla k divided by nabla k transpose times q times nabla k. Therefore, for the steepest descent applied to the convex quadratic problem, we can compute alpha k explicitly. It's easy to find, right? So we just need to plug in all the data, and this is the step that we get for the convex quadratic case. We don't need to apply any numerical algorithms to find the best step size. We have the analytical formula for computing the step size alpha k, and for convex quadratic case, we can easily apply the steepest descent method. For example, if we look at the very simple case that we discussed geometrically for two variables, the problem of minimizing f of x given by the sum of xi squares, so which is just the square of the norm of x, right? Then doesn't matter which point x0 we start with, we can see that by applying this formula, we always get 0 after just one iteration, so we get convergence to the global minimizer in just one step. But of course, again, this is a very nicely structured function. The coefficient for each xi squared is 1, okay? So this is what we call a well-conditioned problem. Okay, so but in general, if we look at how the method converges, we'll see that there is a strong dependence on the condition number of the matrix, and the condition number is related to the magnitude of the eigenvalues of the matrix, okay? So let's discuss the global convergence of the steepest descent method. So in this case, the word global or globally convergent has a completely different meaning from, let's say, global minimizer. The definition of a globally convergent numerical method is given here. We call a numerical method globally convergent if it converges starting from any point. So here we are talking about a numerical method for any problem, not necessarily for an optimization problem, so don't confuse the term globally convergent with computing global minimum. Globally convergent means that whatever starting point I select, my method will always converge to some point. It appears that we can show the global convergence of the steepest descent method, which is a great property, which is exactly what we are trying to achieve here. So the convergence of the steepest descent method here is analyzed for the simple case of the convex quadratic function, but we'll skip the details and we'll just look at the final inequality from which the global convergence follows. When we consider this quadratic function q of x, we can actually show that we have the following relation between q of xk plus 1 and q of x0. So, and let me actually show you what q of x is. So we actually analyze the convergence for this function. Here we can clearly see that the global minimizer is achieved at the point x star, and the global minimum value for this q of x is equal to 0. Because the matrix Q is positive definite, the expression is always non-negative, so therefore as soon as we find a point where the function is equal to 0, this must be a global minimizer. And we can clearly see that for x equal to x star, our function is 0, so x star is the global minimizer. Alright, so but this inequality tells us that q of xk plus 1 can be expressed through q of x0 using this inequality here. And because our global optimal value is equal to 0 here, so because q of x star is 0, right, q of xk plus 1 is the same as q of xk plus 1 minus q of x star, which remember is 0, right? So therefore we can think of this q of xk plus 1 as the error in terms of the objective function value, our deviation from the global optimal value after k plus 1 steps of the method. And this error is bounded from above by q of x0, our function value at the initial guess x0, multiplied by this important expression here. So it's given by 1 minus the minimum eigenvalue of q divided by the maximum eigenvalue of q to the power k plus 1. And we see that the minimum eigenvalue obviously is always less than or equal to the maximum eigenvalue, right? As a result, this expression will give us a value which is less than 1, right? Therefore, when you take it to the power k plus 1, it must converge to 0, right? So our error converges to 0, which means that the method converges to the global minimizer. So this expression here, also similar to the one on the previous slide, it characterizes the errors after 2 consecutive steps. So instead of having q of x0, we have q of xk here. And in fact, this inequality here is obtained by applying this inequality k times for q of xk, then q of xk minus 1, and so on. But when we look at the relation between errors at 2 consecutive steps, we see that the upper bound on the error decreases by this factor here. Therefore, if let's say we had lambda minimum equal to lambda maximum, like we had in the example with the norm of x, right, then obviously this ratio would be equal to 1. The difference here would be equal to 0, and we see that we would have the error equal to 0 in just 1 step. So therefore you would have convergence in 1 step, right? But on the other hand, if this lambda minimum is much smaller than the lambda maximum, then this difference here will be close to 1, and we see that the upper bound on the error may decrease very slowly. The progress that we make with the steepest descent method may be very slow, and this corresponds to these very narrow level sets, such as those that we saw in the illustration of the steps of the steepest descent method. Okay, so and this is when we tend to zigzag too much when we search for the minimizer. So this ratio of the largest and the smallest eigenvalue is a very well known quantity in numerical analysis, and it is called the condition number of the matrix Q. Many methods tend to be unstable when the condition number of the matrix is large, okay? So, and this happens to be the case for the steepest descent. We see that if the condition number is large, it means that this ratio will be very small, and it means that this quantity will be close to 1, which means that our error will decrease very slowly. So in this case, we'll just have a very slow convergence of the steepest descent algorithm.